Good morning. Okay, let's get started. First with the flat slab, and then we're going to go on to something very important, which is the loads on the beam and then the design of the beams. Okay, so let's start with the flat slab tutorial question that you had. Okay. Is my screen visible? Right. So we had this tutorial question, which I gave you. It was a 300 millimeter thick flat slab panel between grids 2 and 3, A and B, as shown on the tutorial question, all right, that you had. 30 MPa concrete, and then you had finishes was 0.75, support an imposed load of 2 kilonewtons per square meter. Right, FCU was 30, FY is taken as 485, and cover is 35, right? Long span was 13.5, and the short span was 8.5. Okay, and then the dimension of the column head was given as 800 up. If you take 2000 minus 400 is 16. 16 divided by 2 is 800, so that means it's 800 by 800, which is a 45 diameter head, which is fine. Okay, so we go on to 4 panels in the direction of the long span and 6 in the other direction, so we can use the simplified rules. Live load is less than 1.25 dead, so that's fine. Okay, so dead load 24 times 0.3 plus 0.75, which is for the additional finishes. Okay, 0.75, 7.95 kilonewtons per square meter. The live load is 2 kilonewtons per square meter, which is given. Ultimate load N is 1.2 times 7.95, 1.6 times 2 gives me 12.74. The effective column head perimeter is 2000 minus, you have to take off 40 millimeters, okay? Because there's no chamfer there isn't a, like this, isn't a, let me just draw what we're talking about. So normally sometimes you have a little bit of a flat part underneath the flat slab. And then you have the chamfer. So we don't have this, okay? We just have that straight, so we have to, since we're going straight up to the slab like that, we've got to take off 40 mils. All right, if you have a straight portion that is not chamfered, then that is fine. Okay, then you take the head dimensions. All right, any questions on that one? If everybody happy with this 40 millimeters, why are we subtracting it? Where it meets the slab directly like that. In other words, the angle is there. But if you have a flat portion normally, and then you have the chamfer, okay, then of course, then you don't have to subtract 40 because you got something there. All right. Okay, 0.2 times the average panel dimension is going to be 2.813 because you're taking the average panel dimension in each direction. 13.5 and 9. Take the average of those, multiply by 0.25. So let's check that. So you got 13.5 plus 9 divided by 2. Your average panel dimension is going to be 11.25 times 0.25, which gives you 2.81325. Let's say 2.813. Okay. So your chamfer 1920. L1 13.5 because you asked to do it for which direction? On the column strip on line B. So this is in the long span. In the long span direction only. All right. So in the long span direction, L1 is 13.5. L2 is going to be 9,000 millimeters or 9 meters. Effective span is 13.5 minus 2/3, 1920. That's your chamfer. Okay, 12,220. Total force 12.74 times 12.22 times 9. So it's the effective span multiplied by L2, 1401.1. You then go to the column strip and the middle strip. Again, column strip, middle strip. This is the area of steel first, the bending moments. Outer support, you got 75%. So you look at your table on page. You go to Greg's table, page 4.9. Okay. Right, page 4.9 in the book, and you see there, for example, column outer support. That's 0.04 and 0.02. All right, since we've got a wall, so we take 0.02. Okay, and then we look at the width of the strip. We took it as 4,500. Okay, because you're taking the 9 meter centers, so 9 meters, and you've got the column strip is equal to 1/4 plus 1/4, and it's equal. So that gives you the 4.5 for the middle strip and the column strips. Okay, middle end, so 75%. That's from the table 17, which comes up on page 410. 75% of it will go. So that coefficient times the force there will give you 57.1. Well, this is per meter, so check. You got 0.02 times 1401, which is 28.02 times 0.02. Sorry, I've just mixed my pages up again. 1 second. Right, so it's 0.02 times, let me write this thing down. So you've got 75%. So you've got 0.75 times 0.02 times, and then you've got F, which is 1401, and then you've got 12.2. Let's check that. So you got 0.75 times 0.02 times 1401 times 12.2, and that gives you 256 divided by 4.5, because you want to bring it to meters. So divided by 4.5, that gives you 56.97, or say 57.1. Okay, any questions? So just to remind you, this is your percentage. This is your coefficient. Okay, this is your F total force. This is your span, effective length, effective span. All right, this is your effective span. So that's your formula, right? In the particular direction here, we're only looking at long span. All right, you were not asked for anything else. Okay, any questions on that one? Is everybody happy with that? Right, then you go to middle of end span.
So just if we go back to the diameter of the column head.
The diameter of the column head. Sure, let me just make this sound a bit loud here on my side. Ugh. The diameter of the diameter head.
So
that 1.2.
You're saying that when the drop is not provided, we must just minus 40 on either side.
Don't mix it up with a drop, right? Because the drop is like this.
Yeah, just that extra.
That's the drop first, and then you get that. Okay, so we're talking about where the chamfer. I'm just trying to word it correctly. Column head doesn't have a vertical component at the end. All right, this is the drop, so let's not confuse the two. Okay, this is a drop, so this is different. That's where you have a drop. That's obviously different, right? Okay, here we're just talking about the column head. Okay, that doesn't have a vertical to it. Okay.
And it'll be 40 all the time.
Yeah, that is given. That's in the code. You subtract 40 moles.
Okay, and then if there is the vertical component, we'll calculate the area and work out the diameter.
If there is a vertical component, then it's fine. Then that's your column head diameter from there. Are you with me?
Okay. Okay, thank you.
That's the difference between the two. Okay. Right, so you've got that. D, you're taking 300 minus, what's it, 25. Let's see, 300 minus 25. Cover is 35 actually. So 300 minus 35 minus, let's say, wrong direction. So this will be the small, larger D. Let's take away 6 and let's see what we get. 259. They've taken 257. So they've taken, let's try 16. I just want to see what he's assumed here. He's got 35 cover. 35 cover, so it's got 300 minus 35 minus, let's say, 8, and that's 257. So assuming a 16 millimeter diameter bar, all right? So it's 300 minus 35 minus 16. Remember, there's a long span, and the long span in flat slabs has the larger depth. Okay, so D1. All right. Then you've got 55%, so it's 0.05. 0.55 times 0.083 times again 1401 times 12.2, and that's divided by 4.5 will give us 173.7. All right, per meter. Remember, these are now calculated per meter, right? So again, D2, all the D's constant here, 257. The first interior support. So at the first interior support, you've got in the column strip 75% again from table 17. 0.063 is the coefficient, so 0.75 times 0.063 times F times 12.2 gives you 179.8 when it's divided by 4.5. 179.8, 257, 257, still D, right? And then you got the middle strip, similar pattern, but you can see outer support now 75, so you've got to put 25 here, 55 in the column strip, so you've got to put 45% in the middle strip, 75 over the first interior support column strip, so 25% is going to go into the middle strip. So accordingly, with those coefficients, you get these moments per meter, and you move on to the calculation of the steel, right? Column outer support, K is calculated M upon FCUBD squared. Okay, let's just take one of them. We'll take 57.1. So you got 57.1 times 1 exponential 6 divided by 1000 divided by D was what? What is D given us? We calculated as 257. 257, and it's divided by 30 MPa, not 25. So it gives us, sorry, let's do that again. I've got 57.1 exponential 6 divided by 1000 divided by 30 MPa, and then we've got the depth being 257 squared. And gives me 0.0288, right? So we get that number, right? 0 over D is 0.95. Anything less than, what did we say? From our graph, I think I told you last time, just make a note on the graph. What's that number? It was sorry. Okay, so it was 0.04 0.3 or 0.04 something. I said when it's less than that. Okay, and of course, don't forget your K prime here, because it is a hogging moment and the risk redistribution has been taken into account. It's the other number, not 0.156, the one we calculated with the redistributed value, right? Okay. Right. Yes.
When you subtract the 16 diameter, so in the exam, you'll be giving us the same one, or anyone can use the one that his think is suitable for the rebate?
What? No, you will assume. You will make an assumption. Okay. All right. AS required 554, and then Y12's at 200, 565. So did you meet the minimum requirements? Let's check. The minimum requirements, you can see the one with an asterisk is the one that needs the minimum, is 390. So that's good enough. 554 is higher. All of them are higher except the outer support middle strip. Okay, Y12 that. So Y12 is a 200. Move onto the middle of the end span column strip, and Y12 is a 250. So basically what you're saying is you've got let's try and just show this. All right, so that's the end. This is where your column is, right? And that's your center line there, right? So basically at this edge here, you've got, and this is the column strip that we're referring to. So you've got 12s at 200, which is going to be there. Okay, at the top. Then you've got 12s at 250 in the column strip, which is going to be Y12s at 250. That's going to be in the bottom, right? Remember here I'm referring to the column strip, eh? And then you've got the first interior support 16s at 100. So that's where you'll have your 16s at 100. I haven't shown the curtailment or anything like that. I'm just trying to indicate the direction of the bar and where it goes. Okay, so that's inside the column strip. And then in the middle strip, that's further in. So here I'll just put it in another color just to separate. So in the middle strip, you've got at the outer support 10s at 200. So you had 12s at 200. Now you have 10s at 200 in the top. Okay, then you've got in the bottom 12 at 75. Okay. And then of course you've got the top steel 16s at 325. Okay, so that's your, remember that's your 13.5 meter span. Okay, so that's your reinforcing. Maximum spacing 249, middle strip 324. Okay, any questions about this? Pretty straightforward. I mean, just apply the tables correctly and that's it. Right.
Sir?
Yes.
So there's no issue when you're designing, like is there no problem when we insert different sizes, bar sizes? Because I chose to only stick with Y10 and Y20 because I thought maybe there might be issues if I have too many different bar sizes. Just clarify that for me.
No, nothing. You can change.
Okay.
I would preferably use a 16. More flexible, right? Okay, easier to work with. It's not bent, so it's not a critical thing. If it's bent, okay, then it's probably preferable to use a 16. If it's not an issue. Okay. Any other questions?
No, with these K values, did you say we need to redistribute?
No, we don't redistribute. The table has already included a 20% redistribution.
So then when we're putting it in the formula for K, we just use the moment and the D squared.
Yeah.
But then it doesn't, if you try like for 57.1, it doesn't give us 0.0288.
You're taking the moment as 57.1. Let me write that down.
Times 10 to the 6.
57.1 times 10 to the power 6 divided by, and here you've got your 30 MPa concrete, not 25, remember? 1,000. Okay. All right, and then your 257 squared. So we're using 25 MPa.
Using 25.
Yeah, just double check.
Okay.
All right.
Thank you.
No problem. Okay. All right, then the next part is the, sorry, just want to check something here. Okay, we don't actually have the solution for the second part of the question, which is the punching sheared column C3. Right. So let's look at that one. Right, let's look at that one there next. By the way, before I forget, I think returning to college is imminent, so I'm sure our test is going to be on campus and our lectures from next week. So please organize your certificates or whatever you need to do to get onto campus, right? I just heard via the grapevine, so I'm just waiting for confirmation official. Okay. Yes.
Before you proceed, please just help me clarify with this. So if you say that the equation has already distributed, the moment has already been distributed. Regarding K prime, do we only take the 0.156, or we have to use that equation with 0.402 brackets and
we work this out for 20%. I've just forgotten what it is. Sorry, just give me a second. We did work it out. We made a note of it that if we have redistribution of 20%, somewhere we work this out and we put a number. Where's my flow charts? Maybe it's on there.
Is it 0.132? Are you referring to that, that value, sir?
That's what I'm saying. Because it'll only be those two numbers. Because for the tables, whether it's a continuous slab table restrained or it's the flat slab, that's 20% has been included, right? So for the, you just use that, but you're not, if you're going to get compression reinforcement in your flat slab, you're in serious trouble. Okay, that shouldn't happen. All right, that mustn't happen. We mustn't have compression reinforcement. Okay.
Okay.
Right, just be careful with that, please. Don't, don't make problems for yourself. Right. Let's have a look at the shear part. I don't have the solution here, so we'll have to work. Sorry, any other questions?
Yeah, so at the bottom there, when you wrote the equation, why did you use B as 1,000 instead of 4,500?
Because we've got here M per meter. So when I calculated the moment, you see here, I divided by 4,500.
Okay, thank you.
All right, so just that's why we put the B in here. And then next to it, you said per meter. If you're going to keep it as 4,500, you'll have a problem now when you go into work out the steel. You're going to get a total AS, and then you're going to have to divide it yourself, etc. So it's easier to bring it to something per meter. Okay. All right. Okay, let's carry on then with the shear issue. Let's go. Just want to start up a new, what do you call this thing? Okay, so we've got V, which is the shear force. Just make a note, please. Please start writing. Right, so we've got V, which is the shear force, which is going to be equal to the total load, which we had. I hope I didn't close that page. That's the value of the load is 12,74. So it's going to be V is equal to 12,74 times Alex, or let me write the formula first so every one of you can follow it easily. N times Alex times Ly. Okay, so Alex is equal to, in our case, and Ly is 9 and 13.5. So 9 times 13.5. So that gives us 12,74 times 9 times 13.5, which gives us 15,479.91. 1547.9 kilonewtons. Okay, then you're looking at the V effective, right? And as before, because you use the simplified thing, 1.15 times V total. Sorry, they call this VT, right? Total shear, which is then equal to 1.15 times 1547.9. 1.15 times 1547.9 is 1780.0, okay, 1780 kilonewtons, right? Then we look at the reinforcement. We look at our average D. We took a D of we used 16, which was, this is probably the average that they used here, right? Because if you take 16, that means you're taking 32. See here, we used the 16, right? I just want to make double sure that that was correct. 300 was the depth. Where are we? $300 minus 35 minus 16, 249. So it's 8,300. Sorry, minus 35 minus 8. I wrote 16 here, but this is actually taking a 16 diameter bar. So it's 16 over 2, right? Which gave us the 257. That's how we got the 257. So what I'm saying to you now, what do I take for the average? Because you're looking at shear, so you take the average depth. We'll assume the same 16, so here we will say the average. Let me just write it here up, sorry. The average is going to be, let's say, 300. We didn't calculate the steel in the other direction, but we were given. It says check the slab for punching shear at column 3, assuming that Y20 bars are used at 175 in both directions in the top of the slab. All right, so at that particular column C3, which we haven't come close to. All right, we haven't dealt with the design of that panel. They're giving us the reinforcement, so they're saying they got Y12s at 175 in both directions on the top, right? Y20s, not 12s. Y20s at 175, center to center, both directions, right? Okay, on the top. So based on that, we're saying D would be 300 minus 35 minus 20. Is everybody happy with this? Anybody confused? So what you're saying is that's the top of your slab. It's your column head. Okay. and your steel. You've got a Y20 there, and then you've got Y20s in the other direction as well, right? Now, whatever distance it's going to, I'm not going to go into that in detail, right? Whatever the distance is, the length is, but we're just interested just to show you. So this is what we're referring to. We're talking about the distance between the two bars. That's our D average, right? So that's the 35 cover on the top. Okay, then you got the 20 diameter bar, and then you got this one. This is also 20, so you're going to the middle of the two of them, right? Okay, and that gives you 300 minus 35 minus 20, 300 minus 55. Okay, 245. Everybody happy with that? Okay. Right, then you've got the, we need the average shear stress, the average percentage of steel. So we go average 100 AS over BD. So it's Y12s at Y12s at 175 in both directions. Let's go back to the tables for steel. On page 412. Right, we have 20s at 175. $1,795, so it's 100 times 1,795 divided by B, which is going to be we're going to use here now 1,000. Remember, it's calculated as millimeters squared per meter. All right, so this is millimeters squared per meter, don't forget. All right, times D, and D we said is 245. That's the D average. Okay, so what does this give us? It's going to be 100 times 1795 divided by 1,000 divided by 245.73. 0, quite a large number, 0.733. Okay, so that's your percentage reinforcement. What is our VC? VC will be equal to 0.75 divided by, I'm using the full formula here, right? Because I've got a different MPa. Remember I showed you the short form when you have 25 MPa, but I've got 30. So don't forget, we have to use a full formula then. 1/3 times 100 AS over BD. We've worked this out already. We just put in the number there, 0.733. Times, all this is raised to the power 1/3. And then we're multiplying by the actual H divided by 400 divided by D, sorry. So 400 divided by the actual D, which we said is we're taking D average 245, and this is raised to the power 1/4, which is 0.25. Let's see what that gives us. So you got 0.75 divided by 1.4 times brackets 30 divided by 25 raised to the power 0.333. I'm just using 0.333 instead of 1/3 times, bracket again, you've got 0.733 to the power 0.333. Oops, sorry. 733. 4.333 times I've got 400 divided by 245. That's raised to the power 0.25. And I get 0.58 newtons per millimeter squared. Do you get the same number? Do you get the same thing?
Yes.
0.58 newtons per millimeter squared, right? What's our load perimeter? Our first load perimeter, because we got the column head. Don't forget we took out the 40, right? So we're going to say, what was it? 2000. This was circular. Yeah.
In your equation, that brackets and then 0.733 brackets 1 power 1/3.
Yeah.
Is there any particular reason for that? Because I had it divided by BD, which gave me a totally different answer.
No, I already put it in here. It's already divided by BD here. So I already did that here.
Okay, I'll try it out and see, because
You know what I'm saying to you? Here's your 100 AS, right? Divided by BD. So did you divide it twice by BD?
okay.
Right, you know what I'm saying? I think you've divided it twice.
I think so. Yeah.
Right.
All right, I'll check it out. Thank you.
All right, so now you've got the load perimeter, so it's circular, remember, it's not a square anymore, all right? So what's the perimeter of a circle? You've got our diameter, we have to take off that 40 millimeters, remember? So we're looking at it from there to there, which is going to be 2 meter diameter column head. So you've got 2 meters minus 0.04, correct? Which is going to be 1.96. I think we used it earlier, if I'm not mistaken, in our calculation somewhere on the previous thing. Yeah, 1.92. There you go. It's subtracted from both sides, so 0.04 is going to be 0.08, right? So you got 1.920. Okay, so that's my column head. Now I need we've got the diameter of a circle. Sorry, just want to confirm something for you quickly. 1 minute. So, sorry, coming back, I just want to find out something. It's just 2 times pi times r. So 2r is d, right? So pi times diameter, if you like, it's going to be pi times. Okay, sorry, bit of a break there in the connection. I times 1.92 is 6,03. You get that? Do you get the same thing? Meters, right? So what's my area? That's the load perimeter. Okay. Oh, by the way, we're supposed to have said something here. This 0.58 is less than 0.8 FCU square root sorry, I forgot to complete this. 0.8 the root of FCU. So we've got 0.8 times 30. 4.4, right? 4.38 something.
Yes, 4.38.
Okay, so that's fine. Now we've got the load perimeter. We need the VO is going to UO. So this is UO if you like. Yes, I'm listening.
Why did you exclude the 2 by the load perimeter when calculating?
Which 2?
The 2 pi radius.
No, because 2R is diameter.
Mm.
So I should have, if I want to use radius, it's going to be 1.92 divided by 2.
Okay.
See, here I'm using pi d.
Yeah,
Okay.
I see.
Okay,
So
d is 2 times radius. All right. So UO. So what's my VO going to be? What is my VO going to be? O is going to be along that perimeter. I've got the total force, which is sorry, the 1780 times 10 to the power 3 divided by the perimeter, which is 6.032 times the depth, average depth, which is 245, and that gives us 1780 exponential 3 divided by 6.03. I need to use meters, so I mustn't have a point there. It must just be 6032 millimeters. Okay, so 1780 exponential 3 divided by 6032 divided by 245, which gives us 1.2. Get the same thing?
Yes.
Right. 1.2. So this is now a problem. 1.2 newtons per millimeter squared. I just want to make sure I put everything in correctly. 1780, right? And where is it? The shear resistance is 0.58. So it's much more than that. Okay, therefore we need reinforcement. Okay, shear reinforcement is going to be required. Right, sorry, this is still less than the maximum, but we have to check it at the first perimeter. This is less than the maximum, which was 4.38. What am I writing here? Sorry, I meant 4.38. So this is the first perimeter, 4.38. Right, so it's less than the maximum. It's less than Vmax. Okay, we go to the first perimeter to check that. Let's go to the first perimeter. Okay, first perimeter. Right, so on the first perimeter, we've got U changes. Now U1 is going to be equal to 4 times 1920 plus, not, sorry, Remember, we're dealing with a circular column head, not a rectangle square one. So it's going to be pi times, and we've got 1920 plus 3d, 1.5 d on each side, right? And that is going to be, what is that? Pi times 1920 plus 3 times d. We took the average d is 245, right? So 3 times 245, 735. Okay, so U1 is equal to 1920 plus 735 times pi 8.34. 8341 millimeters squared. Sorry, millimeters, not millimeters squared. We haven't calculated the area yet. All right, so that's the first perimeter. Then you've got V1 is going to be equal to V effective, which was 1780 times 10 to the power 3 divided by 8341 times, what is this? 8341 times the depth, which we took average as 245. So 1780 exponential 3 divided by 8341 divided by 245, which gives me 0.87. 0.87. You got the same number? You also get 0.871. Now this is greater than VC 0.58. Therefore, reinforcement required. Okay, all right. So at the first perimeter, then we go to the next perimeter. So remember, go to in the book page. Sorry, I just want to give you the page number where we check the next perimeter is 0.75 and 0.75, so 1.5 D. So U2, so this is the first perimeter. We've got a problem. Let's try U2 and see if we need reinforcement in there. So it's going to be pi times, this will now increase by 1920 plus, sorry, 1920 plus, hello, 1920 plus 735 plus, this is going to be 1.5 D now, right? Because this is the next perimeter. See, the first one was 3. After that, you increase by 0.75 on each side. So that is going to be pi times 1920 plus 735 plus, it's going to be 1.5 times 242, where's it, 245? 367.5, 367.5. We're trying to see where we've got to put reinforcement in for how far, okay? So that gives pi times, in brackets, you got 1920 plus 735 plus 367.5. Okay, and that gives me 9495. Okay, 9495.5. Right, so that's my U2. So let's check my V2 now. is going to be 1780 times 10 to the power 3. Okay, divided by 9495.5 times 245, and that gives us 1780 times, 1780 exponential 3 divided by 9495.5 divided by 245, which gives us 0.76. Still, we're running into trouble here, 0.765, which is also greater than 0.58, okay? So we're going to carry on like this to the next perimeter. So what's going to happen then is, if we look at the first perimeter, 0.871, if we see what is 1.6 times 0.58, it's 0.928. So what I'm saying to you, if I take that and I multiply it by 1.6, it's equal to 0.928. Okay, and since V is 0.871 is greater than this, greater than VC but less than, so we're talking about the situation we've got V greater than VC but less than 0.156, 1.6 VC. Okay, so in this case we have a formula which we have to put reinforcement in for, which is that on page 4.19. I'm just going to write here refer 4.19. Okay, so what I'm saying to you is we're going to have to put in links. All right, now when we put in links here, if you look at the sketch that Greg's got on page 4.19, not the easiest thing to do is to put a link like that. It is better to do the following. It is better to do the following, where you want to actually hook like this, right? So put single legs like that. Don't try and use this one. Okay, this is a preference, right? Avoid this one. It's going to give you more complications, right? So I would like you to just see where you're going to stop the reinforcement and how you're going to put the reinforcement in and what the area of this is. The links are calculated on ASV. That's great. The area of steel links, sorry, let's write this neatly. Sigma ASV. Okay, must be greater than V minus VC divided by U times D divided by 0.87 FYV. Okay, so for example, I'm just going to take the first one in the first band. We still have to check V3 and see where we can stop this reinforcement until we get to where we're less than 0.58, right? So you got V minus VC U, that's the perimeter, times the depth, divided by 0.87 FYV. So this is the total amount of links that have to be placed in there, right? So let's just take that one just to show how. So it's 0.871 minus VC, which is going to be 0.58, right? Times, you take that difference times the perimeter, which we had as, take the first perimeter 8341, right? And then times 245 divided by 0.87, and let's say we're using Y10, so we'll just take it as 450 for now. 15, I'm just trying to get, sorry, 1518. Okay, so what does this mean? What it means is when I look at my, I'm just going to do it roughly, So you're looking at your column is, where is it? 400 diameter column, right? It's not to scale, so just bear with me. And then you've got the column head, which was 2 meters, right? So underneath, you had the column head, which was 2 meters, okay? Your column strip, which was, what did we say, 4,500, right? So your column strip somewhere there, 4,500. You've got 10s at, we need to find the first perimeter, which is 0.8, what is it, 192 plus 735 plus 1920 plus 735, 2655. Sorry, I'm don't have something. Maybe I can do this. Let's see. Draw little circles. See if that works. It's just okay. Does that look like a circle or like an egg? Okay, all right. More like an egg actually. All right, never mind. Just so you understand what we're talking about. Shape, fill, put nothing. And let's just give it, so that's the first perimeter. I'm going to take off these lines, right? These other ones, just so you understand where we're going with this thing. So that's your first perimeter. Sorry, let's put that in dotted because it's underneath, remember? Okay, and then we'll copy that. I will just make it bigger for the next one. Sorry, I should be drawing this thing to some kind of scale. But anyway, for now, just to give us an idea of what we're talking about. And then we've got the next perimeter. So we had how many perimeters we were still in trouble with? So the next one we had, sorry, 2655 was the first one. So first perimeter there was at 2655. So in other words, from there to there was 2655 divided by 2, 1327.5. Then the next one went out. Okay, so the next one goes out how much? And that's U2 we called it, which was 1920 plus 735 plus 367.5. 1920 plus 735 plus 367.5, 3022.5, 3022.5. So the next one's at 3022.5. If I take that divided by 2, I've got 1511. 1511.25. Just going to say 1511, right? Sorry. Let's just round these off. 1328. 1511. The next one will increase by how much? I haven't put it on yet, but the next one's going to increase by and another. Okay, so that's 0.75 on each side. So it's going to be 1511 plus 0.75 times 245, which gives me what? 1511 plus 0.75 times 245. and that's 1694. Okay, so the next one's 1694. Last one now is 1694, not the last one we actually have to check. 1695, let's say. All right, we still have to check where VC is greater than V. All right, but what I just want to get you to understand something. So we've got 10s at 175. You have to do this to some scale, and I'm not, so that's the problem. But just to illustrate, so you've got, well, what would you say this is? We said this is, sorry, I should have had some kind of graph paper to work with first. 1328. Just trying to see if I can match some scale to what I've drawn. Give me a minute. 1328. 1328. Okay, let me. 1 second, guys. I just want to get this thing to match some kind of scale here. Okay. It's going to be slightly bigger. I'm just trying to get a scale for myself, right? 1.3 roughly. And then the next one's going to be 1.5. Oops. 1 meter 500. Sorry, I'm trying to put this thing into the air here. That's why. That's more or less okay. Let's see. Okay, on that side, and then the next one's 1.7 roughly. 1 meter 700. Just pull that in slightly. Should be okay. Let's make this slightly inner kind of thing. Right, okay. Right, now we got 175. So what is 175? I'm just trying to, we had 12s at 175, right? Sorry guys, just bear with me here. So I've got 350 will be about there. For 350. So it's probably just better to do it as 350s and then split it in half. 350s first. Right, I'll just do 1/4 of it so we can see what's going on. Sorry guys, just give me a minute here. Trying to keep my drawing off my screen. Okay, so in the middle, roughly there. Need another one here, 350. 1, somewhere down here. Okay, is that right? Let's check. Okay, so basically what we're saying is you've got, I'm just showing one part of it, right? So you've got these bars running across. I need to move that one up slightly. So your reinforcing bars running in here on the top. Your 20s at 175 centers. You have to do this accurately, so it's very time consuming, as you can see. Ideally do it in CAD or something, it's much quicker. or use some kind of graph paper that you can scale. Oops. Okay, and I'm just trying to draw one side, so just bear with me, please. Okay, it's a bit difficult to get it accurate here, but let's just be as close as we can be. So seems to be a bit big. To just move it. And then I'll put the ones in between just now. Okay, and it will go on like this. And then right, so what I want you to do is draw this to scale, obviously. Right, and now you're going to, the other side's going to be the same, so let's see if I can just do a copy and pasting here. It's not, mine is not accurate, obviously, because I'm working off on the circle, man, on the bar. So I'll delete some of these things. Sorry. Replicate one of these. Right, close enough. I'm just trying to show you what are we talking about there, right? So basically, and we can do the same with the bottom. That one just needed to move up slightly. It's not very accurate, but it'll give us an idea of what we're talking about. Okay, enough. Let's just copy that. Paste. So I'm going to get rid of that circle from there. Sorry. That, and then just take all of these again. Apologies. It's a lot easier when you do it by hand drawing, when you use CAD. I'm just trying to do the best I can here. All right, so that's roughly your reinforcement going around those perimeters, okay? Right, now you got to put in your links. So where do your links go? Your links go in between your reinforcement requires, if I want you to turn to page 419, when on a particular perimeter V is greater than VC, reinforcement is required to resist the shear stress. This reinforcement should be evenly distributed in a zone of slab between that perimeter and a perimeter 1.5D inside of it. Okay, so you're starting here in the first perimeter and you had a problem, so we needed, what did we say? Where's the reinforcement here? Where are we? 1,518 if you divide it by 157. So ASV would be equal to 1518 divided by 157. 1517, I'll explain what I'm doing now. 1518, sorry, divided by 157. No, not 157. What's 110? 1Y10 bar. I'll just check my tables, steel tables. Give me a second. We need to use the ones that in the book somewhere for beams. So 1Y10 is going to be 78.5. I'm not using two legs, 78.5 is the value of 1Y10. Okay, or the area of 1Y10. So 1518 divided by 78.5, that's 1933.719. So we say 20. So I need 20 links. Okay, now these 20 links have to go in here. So where do I put them? For example, it's got to go within those perimeters, right? So let's say 20 links. This is a bit of a, it's going to go, let me use a different color here now, right? We're going to put it in, for example, I'll start with that one. Next one, we might just get in. Next one will go. Let's see, 1, 2, 3, 4. Okay, and then we'll have to space them out in this direction similarly. 1, 2, 3, 4. Okay, and this will be right round. So these little dots are what I'm showing you. You've got the top steel, and basically you've got a bar in the top. And what you're going to do is you're going to have to bottom steel as well. Sorry, some bottom steel that you've got there. And this is where your ability to detail starts to come in, because remember it's got a hook there and it's got a hook onto a bottom steel as well. Right, so you need to position them into that thing there. So I'm going to have to draw this neatly. I want you to try it as well. Okay, and just see what's the best position we can put these links in. But we need 20 of them between the first and the second perimeter, and then we have to check second perimeter, what happened, how much reinforcement do I need, and then I can go 0.75, use what is inside 0.75 of 1, and then move it onto the next perimeter. So it's a bit tricky, but we need to do this, okay? All right, so we need, and you'll end up putting more links than what are required. Okay, so I want you to try this out and see, draw it neatly and see how you're going to position it. Get back to second perimeter, check the ASV required, do the third perimeter, check if the ASV is still required. You continue to calculate until you come to a perimeter where it's less than VC. When it's less than VC, then you stop at that perimeter and then you have to put in, check ASV for everyone. Obviously it becomes small, it becomes, you'll need less stirrups as you go out. But this is the headache that you have when it comes to this. Now, the other option would be to provide a drop. So if you want to avoid all of this, you've got two other options. And one option is to increase the depth. So to avoid, right, to avoid the links, right? You got two options. One is increase D, right? And the second one is introduce a head. So what you're going to do is you do that, introduce the head, and then you have that. Okay, so by introducing a head, what you've done is you've increased the D. Right, it's another way of increasing the D. One is to just make the slab thicker, okay, and keep your column head without a drop. But that is going to increase the depth across the slab everywhere. So you have to play with the numbers and see what's most convenient. All right, I won't take it beyond this. We'll stop here with this part. Any questions? But I'd like you to go through this on your own and check which perimeter you can stop it at. So you start with the first one, and then after that, you're increasing it by 0.75 D on both sides to get a new perimeter. Do you understand what I'm saying? Now you need to find the perimeter at which you don't require shear links, right? And once you've got that, then you can work backwards and say, all right, I need so many stirrups or links in this set, so many in that, so many in that, so many in that. Not straightforward, especially when it's circular. When it's rectangular, it's a lot easier. When you got rectangular ones, the detailing becomes much, much simpler. Okay, if you have to take the circles out and you put rectangles, you can see that it works out very nicely then, because then you've got the grid quite nicely working out. Here you see, because your perimeters are circular, but if it's rectangular, then your perimeters are like this. And it ties in with your steel quite nicely, so you can fit it in, like you can say, okay, I'm going to put it in, you know what I'm saying, wherever they meet inside that perimeter. So that's a lot easier to achieve than in a circular one. Okay, so when it comes to a rectangle, much, much easier. Okay, all right. So anyway, I would like you to have a go at this just for the purposes of preparing you mentally as to how you have to deal with an issue like that. Okay, and then we can look at the solution. I'm not in a hurry for this. You can do this by the weekend. Okay, so no urgency with this one. Okay, but try and achieve it by this weekend. Let's have a look. Shear, not for the this detailing, etc., not for the assessment in the test. Basically, you just want to know if shear is a problem or not a problem is really all I would want to know. Beyond that, this kind of detail, it'll take too long in an assessment, okay? Right, if you're writing the supplementary or something, then maybe we can talk about it for that one. Okay, so let's take a small break here. Any questions, guys? I know it's quite a challenging one that you have to sit and draw and work it out. It's not complicated, it's not difficult, but it's just very challenging because you've got to sit and sort it out nicely. Any questions?